Let's put all of what we've learned about the one-sample z-test together. Okay, suppose you're a data analyst for a labor relations organization, and you're responding to claims that most American workers should be paid less. So a CEO of a large private firm is claiming that the average number of hours worked per week is 37 hours. So the CEO is claiming that the population mean equals 37. And the CEO is using this claim to say that workers should be paid less. Well, you want to examine the CEO's claim using the one-sample z-test on a random sample of data. You want to see, is this CEO correct? So here's our sample of data. It's based on real data from the American Community Survey, a random sample of Americans conducted by the US government. The sample size here is 343 respondents, so this is actually a subset of the American Community Survey. We're going to look at this variable of hours worked per week. Before you begin with a hypothesis test, you should consider the preliminary aspects of the test. In this case, we should consider the target population and the parameters of interest. Are you really interested in the mean or something else? In this case, our target population is all employed people in the United States. We have a random sample and we want to generalize or test some claim about that population. Then, in this case, we want this sort of mean. That's our actual parameter of interest. So we're really trying to test the CEO's claim about the population mean for hours worked. And since the sample size is greater than or equal to 30, we're going to use the sample standard deviation as an estimate for sigma, the population standard deviation. We're going to conduct a one-sample z-test. The idea is that the one-sample z-test is based on modeling the sampling distribution as a standard normal distribution. First step is to state the hypotheses. Again, the null is almost always an equality, where mu naught or mu subscript 0 is some claimed value for the population mean. That's an equality. The alternative for a two-sided test is that the population mean does not equal that claimed value. In this case, the CEO is saying the hours worked per week for employed Americans in the population is 37. Well, that's the claim we're testing. And then our alternative hypothesis is that the CEO is wrong. Either the number of hours worked is less or it's greater, but that CEO is just incorrect. So we're conducting a two-sided test. For step 2, we choose a significance level alpha. Now recall, of course, that researchers use an alpha of 0.05. By convention, it's the criterion for statistical significance. So we're going to use an alpha of 0.05. But of course, this is not a law of nature. This is a social construction. It reflects sort of the conventions within a particular academic field. 0.05 is very commonly used in the social sciences. For step 3, we then calculate the test statistic. The test statistic for a one-sample z-test is given by the sample mean, which is a point estimate for the population mean. So we take our sample mean, subtract the claimed value of the population mean, and we divide by the standard error, where the standard error is sigma, the population standard deviation, divided by the square root of the sample size. Since the sample size is greater than or equal to 30, and we don't know the population standard deviation, we're going to use the sample standard deviation as a point estimate for the population standard deviation. That will allow us to calculate the standard error. The z-test statistic, all it's saying is that, okay, the CEO thinks that the sampling distribution is centered on mu naught, on this claimed value of the null hypothesis. So if that CEO is correct, right, how far away is our sample mean from that claimed value of the population mean on that sampling distribution? Right? If that z-test statistic, if it's really extreme, right, it suggests that we should reject the null. Right? So let's actually calculate a z-test statistic for the CEO's claim. We can look at the summary statistics, and for calculating the z-test statistic, we will need the sample mean, right, which is 38.49 hours per week worked, the sample standard deviation, which is 13.19, the claimed value of the CEO for the population mean, which is 37 hours per week, and then we have the sample size, which is 343 respondents. So we can calculate the test statistic for the one-sample z-test. The test statistic, right, using the sample standard deviation for the population standard deviation, we obtain a standard error of 0.71, and so the test statistic is in fact 2.1. Right? All we do is we're taking the sample mean, of 38.49, subtracting out that null value, that claimed value of the population mean by the CO, we're dividing by the standard error of 0.71. What this tells us, right, it's telling us if the null is true, if the sampling distribution is centered on what the CO is claiming for the population mean, right, then our z-test statistic, it's telling us that our sample mean is, it's relatively extreme, right? It's quite a bit higher, it's in that far right tail of that distribution, right? So let's visualize this. This is the standard normal distribution model of the sampling distribution. This, we're assuming that the null is true, so that's equivalent to saying, okay, we think that the sampling distribution is going to be centered on what the CO claims. That's our null, right? Well, if that's true, this is where our sample mean lies, right? It lies quite a bit above that population mean claimed by the CO. And we use that location of the z-test statistic on this standard normal distribution model of the sampling distribution to make decisions, right? To either reject the null or fail to reject the null. So we're going to do this by the critical values approach as well as the p-value approach. So let's first look at the critical values approach. The critical value is based on the significance level of alpha. So for a two-sided test, right, where the alternative is that the population mean does not equal the claimed value, if the z-test statistic in absolute value is greater than or equal to z alpha divided by 2, then we're going to reject the null. So for alpha of 0.05, the critical value of z alpha divided by 2 is 1.96. Well, since our z-test statistic is about 2.09, 2.1 with a rounding error, we have a value of, an absolute value of 2.09. That is greater than our critical value of 1.96. Thus, we reject the null that the population mean is 37 hours per week at the alpha of 0.05 level. To put it another way, our z-test statistic, it lies in that rejection region on which we base our critical value. All right, so we can look at this. So for a two-sided test where a z-test statistic is roughly 2.1, 2.09, if we have a z-test statistic greater than 1.96 or less than negative 1.96 or equal to negative 1.96 or positive 1.96, if it lies in those two tails, right, then we reject the null. And in fact, in this case, our test statistic is greater than 1.96, so we reject the null. We can also use a p-value approach. The p-value is based on the value of the z-test statistic, and it can be computed from statistical software found in a table. For a two-sided test, right, where the alternative is that the population mean does not equal that claimed value, the p-value is simply the probability of obtaining a z-test statistic greater than or equal to the one we obtained in absolute value multiplied by 2. Right? We multiply by 2 because we want to take into account the fact that we might get an extremely negative z-test statistic or an extremely positive z-test statistic. It's a two-sided test, right? So we're interested in both sides of that distribution. Using statistical software, we find that the p-value is 0.0358. We compare that to our level of alpha of 0.05, and we find that it's actually less than 0.05, so we reject the null that the population mean is 37 hours per week at the alpha 0.05 level. Again, we can visualize this, right? Here's a two-sided test with a p-value, right? Here, in absolute value, our z-test statistic of 2.1 is simply 2.1. The probability of obtaining a z-test statistic greater than or equal to the one we obtained in absolute value is about 0.018. That's given by that sliver of area under the curve of the standard normal distribution model on that right-hand side. All right, then what we can do is we multiply that by 2 because we're interested in extremely negative or extremely positive z-test statistics. And we have this p-value of 0.036, which is less than 0.05. And so we reject the null that the population mean is equal to 37 hours per week at the alpha 0.05 level. So we can use critical values or p-values to make a decision. At this point, we're ready to state a conclusion. Using the critical values approach, right, we find that our test statistic in absolute value is more extreme than 1.96, which is our critical value, so we reject the null. Using the p-value approach, we find that the p-value is 0.0358, which is less than 0.05, so we again reject the null in either approach. And you'll find that this is the case. The critical values approach, the p-value approach, you should come to the same conclusion. Right? regardless of what approach we take, we say the CO is in fact incorrect. I also recommend that you calculate a confidence interval. So a confidence interval for the population mean is given by the point estimate plus or minus z alpha divided by 2 times the standard error, where again the standard error is the population standard deviation divided by the square root of the sample size. Using our sample standard deviation as a point estimate for the population standard deviation, we find the standard error is 0.71. That's just the standard deviation of this sampling distribution that we expect to find. And we can calculate a 95% confidence interval. So we find that the confidence interval is 37.1 hours per week to 39.88 hours per week. Since this doesn't include the claimed value of the population mean, which is 37, we reject that null hypothesis versus the alternative that the population mean does not equal that value of 37. And we reject this at the alpha of 0.05 level. That's because a 95% confidence interval is based on 1 minus alpha times 100. So the 95% confidence interval is based on the idea that we're going to make a type 1 error about 1 out of 20 times. So there are a few things to know about conducting a hypothesis test, in particular with the one-sample z-test. In general, hypothesis testing can be conducted with critical values, p-values, or confidence intervals. A test statistic is simply a standardized measure of how far our data lie from the claimed null value on the sampling distribution under the assumption that the null is true. Depending on the alternative hypothesis, tests may be two-sided, left-sided, or right-sided. And with that, we conclude our discussion of the one-sample z-test and the basics of hypothesis testing.